Hello world, it's me. Occasionally, usually on older schematics, you'll see some logic gates that have inversion bubbles on the inlets. And sometimes they also have them on the outputs as well. For example, this is a portion of the schematic for this board. This is an Intel ISBC 8005, which is one of their very early base, absolutely stripped down models of the 8085 single board computers. And we can notice that on A28, it's drawn with inversion bubbles on the input, and the same with A29, and A23 has inversion bubbles on both the inputs and the output. And I was helping someone resurrect one of these 8005 single board computers the other day, and I sent him these schematics. To his credit, he tried to understand the schematics, but one of his first questions was, why are they making this so confusing to understand? They're using gates here that don't even exist. What's with these inversions on the inlets of these gates? In that email, he sent me some links to some of the explanations he'd seen on the internet, and they ranged from just missing the mark, like they were understanding the notation, but they didn't quite understand why it was being used, what the concept was. And other explanations were just complete and utter nonsense as to why gates have inverters on the input. He did understand that if you have a higher integrated device like a SSI latch or any medium scale or large scale integrated device, it means that the active input is low if there's a bubble on it. So for example, with this 74106, this preset has a bubble on the inlet, and that means that that is active low. And he understood it when it was in one of these MSI or LSI gates. So after that interaction, I searched YouTube and came to the conclusion that this is a widely misunderstood topic, and the topic is certainly worth a video. In this video, I'm going to give my perspective as to why we use this form of these AND or logic symbols, and what's going on with the inversion bubbles on the inlet. Is it monkey shine? Is it malice? Or is it some sort of madness? Why did we do this when we were drawing circuits? So, long story short, this notation is simply a method to functionally, rather than logically, describe a circuit to make it easier to understand. And if you know how to interpret their use, it can really help simplify a design, help you understand of a circuit, and make it much quicker to talk yourself through the various logic scenarios. But unfortunately, if you don't cop on to the intent, these inversions on the inlets and outlets can really make the circuit more difficult to understand. Now, I learned this as assertion level logic, but negative logic is probably a reasonable working term that somewhat describes what's happening. But the term assertion level logic is nice because it infers a meaning to the interpretation of the gated signals by function. Not necessarily by their voltage levels, but rather by their function. We're primarily interested in when that signal is asserted. So let's back up a bit and look at the truth table for an AND gate. I took my niece shopping at Costco the other day. She's a kindergarten teacher, and she accidentally left a 24-pack of Sharpies in my car, so we've got lots of colors to work from now. Okay, in an AND gate, we have the inputs, input A and B, and the logical output is going to be A and with B. And in standard practice, a 0 means the signal is low, and a 1 means that the signal is high. So for example, the only time that the signal goes high is when both input A and input B are both high. So this is going to be a 0, this is going to be a 0, that's going to be a 0, and this is going to be a 1. Now for convenience, we write these as 0s and 1s because they're quick to write. But this isn't called a 0 and 1 table, it's called a truth table. So let's write it more formally as a truth table where the entries are either true or false. So the exact same thing, only instead of 0s and 1s, we're going to say that this is false and this is true. So with A and B inputs false, then they have 0 volts on the output, so the output is false. If B is true, A and B, this is still false, this one's still false, but this one here, if A and B are true, then this output is going to be true. Okay, so this is the exact same truth table we had before. It's just that instead of the zeros and ones, we're now going to call these trues and false. Now let's apply these to actual signals. Say the read and write strobes that we see every day from our favorite processors. Typically, these signals are active low, meaning, of course, that normally when they're not doing anything, they're at VCC, say +5. And they go to 0 volts when the read or the write is actually happening, like we see in this waveform. Read is normally high. When we're actually doing a read, it goes low. And the way that they're noted, they'll either be something like a read with a slash in the front, or it'll be a read with an asterisk after it, or it'll be a read with a bar over the top. These all mean that it's active low. So let's do a truth table for an AND gate of the read and write. And this is nothing that you don't already know. We have the active low read and write signals, and so their logic and of that read and write just go like this. If they're both low, then that one's low. If that one is high and that one's low, it's low, that's low, and that's 1. Okay, this is just the same AND truth table that we had before. But more formally, as a true and false table, we have a choice. When, for example, the read signal is at 5 volts, is that logically true or functionally false? What do we want to call that? Those both mean the same thing. It's logically true, it's at 5 volts, but it's functionally false because we're not in a read state. So there's a couple of ways that we can do this. Which of these truth tables would you say is correct? Let's look at the second row in this truth table over here. Read is at 0 volts. It's at logically low, or 0. And while write is at 5 volts, it's at logic high. The logical AND of this read and write is going to be false. It's going to be 0 volts. So if we think of these signals in terms of their voltages, this is the truth table we're going to get. But now instead of thinking these as voltage levels, let's think of these as what that signal is actually doing. So now if we say that our read is at 5 volts, so again, let's do the second row here. If our read is at 5 volts, that means it's false. That means we're not doing a read. And so if the read is at 5 volts, but the write is at 0 volts, the write is true because we're actually doing a write, it's at 0 volts. Read and write in that case would be false. If we were to do a read or write, it would be true, meaning that we are either doing a read or a write, or in this case, we're doing both. So in this truth table, by true and false, we mean is the signal asserted, or is it active? Or in loose terms, that signal, when it's true, is doing whatever we've tasked it to do. So that signal, if this is true, it means that we're actually writing. This signal, if it is true, it means that we're actually reading. So for clarity, let's please call this an assertion level logic rather than negative logic. Because if we could just call this negative logic, it can get a bit confusing later on. And these two, meaning either voltage level logic or assertion level logic, can live together on what's called a mixed or a combined logic circuit diagram. And they can coexist quite well if we're able to keep them apart in our mind and we know which logic is being used for what gate. So if we go back and we look at this ISBC 8005 schematic, we have some that are normal logic. Like here's a normal NAND, here's an AND. And we have some that are assertion logic. Like here's one that has inversion bubbles on the inlet of this OR gate. Here's a schematic for a Prolog 7801. This is an 8085 CPU. And most of the time, they're using assertion level logic. So you can see this one has bubbles on the inlets and the outlets. And sometimes they're using normal logic. This one has no inversion bubbles on the inlet, and it's just a regular NAND gate. Other times, this is another one from Prolog. The only thing they use on this schematic is assertion level logic. For example, they even use assertion level logic on this inverter, where they showed that it's got a inverter on the inlet rather than as we would normally have it on the outlet. So they want us to think of this in terms of assertion level, not in terms of logic level or 0 and 1 or 0 and 5 volts. So when we're using assertion level logic, let's look at a truth table, how we would do this to make it extremely clear what kind of logic we're using. So if we do that last truth table we did, this one, assertion level logic, because here we had the signals as being shown as inverted. This was read with a bar over it, so these were kind of inverted, but then we said that 5 volts was false. So we can redo that truth table where we actually call this what the signal is. So if we said that this is currently reading, currently writing, and the answer is we're currently in a read or a write. Okay, so if we're not currently reading and we're not currently writing, then we're not in a read or write. These two would be true, true, and in this case we are in a read or write. We're actually in both. So any bonehead can understand this, and there's absolutely no room for confusion if we were to go to all the trouble to write the truth table like this. If you think of assertion level logic, hopefully you can appreciate that there are many, many times we're thinking of a signal and what is actually happening with that signal rather than its voltage greatly helps with its understanding. And that's what the circuit designer is trying to do when they draw something like this AND gate that has inversion bubbles on both the inlet and the outlet. When we look at this gate, the designer wants us to think that this is actually a functional AND, and he's using assertion level rather than the actual logic levels of these signals. And he told us that by putting these inversion signals on the inlets. And sometimes you'll see the inversion signals on the outlets also. But if you see an inversion signal on the inlet, an inversion bubble, and if you see these bubbles on the inlet, you should be thinking of that signal in terms of its assertion level rather than its voltage level. So this schematic again is from the Prolog 7803. This is a Z80 based single board computer. If we look at this part of the circuit, this is U7. U7 creates an active low reading or writing signal. So U7 pin 11, if we were to give that a name, it would be called reading or writing. Means that if that signal is active, the processor is either reading or it's writing or both are active. And that's created by functionally ORing the reading and writing signal. So I called this reading and writing, but this is actually read with an asterisk after it, which is active low, and write with an asterisk after it, which is active low. The little prime on that simply is to keep it separate from another read and write. So for example, here, the read and write without the prime is the buffered version, and this is the prime version, or what comes before the buffered version. So you can ignore that little prime, that apostrophe, because this just is to keep the signal separate. It doesn't mean anything in terms of the assertion level. The only thing that means anything in terms of the assertion level is that asterisk there and the inverter on the inlet of this OR gate. So just like that last truth table that we did, if we are reading or if we are writing, so if either input is true functionally, then the low output of this functional gate is going to be true. Of course, from a voltage perspective, the signal being yes or true in this case means that 0 volts, or whatever we would think of as being a logic 0. And a value of no or false means 5 volts, or what we would normally call a logic 1. So it's important that we would call this U7 by its logical function, which is not the same as a logic gate. As a functional OR, this OR symbol, having invert bubbles on both the inputs and the outputs, is simply referred to as an OR, just as if it were an OR gate, but with the understanding that with the assertion level logic, this is a functional OR. So in the end, that's the meaning of the invert bubbles on the input. It's how we know whether the design is using normal positive logic or if they're using assertion level logic. As an example, to read this part of the circuit, it'd go like this. U7 is ORing together the read and the write inputs, and the U7 output is currently reading or writing. Down here at U8, the first input is active when the Z80 currently has an I/O request. That's the I/O request signal. The second input is active during input M1 when the Z80 is currently in the M1 cycle. So this output of U8 means that the Z80 is currently in an M1 and there's an I/O request, which on the Z80 only happens during an interrupt acknowledge. So this signal, which is asserted low, is an interrupt acknowledge signal. Now that goes into this U7 gate that says we OR together the currently reading or writing signal with the interrupt acknowledge signal, and if either of those are true, then this output goes true, and this is the strobe called machine cycle synchronize, or MC sync, which again is active low. Here's another case where they want us to think in terms of functional logic. If the inputs to all of these chip enables are active, and we can see from the asterisk that these are all active low, these are functionally ORed together. So this tells us that if it's an onboard chip select is true, so if any of these are true, in this case 0 volts, they're ORed together, and this final output, OBD, will become true. In other words, if the memory accessed is onboard, then the onboard signal will go true, which is 0 volts. So you can probably understand that if this is considered to be an OR gate, this would be considered a NOR gate, but then we invert that right afterwards. So this is actually just equivalent to an OR. The reason they showed this as a separate gate is because it's actually a separate logic chip. Now I know you're saying, or at least you should be uncomfortable with the idea that typically these sorts of gates don't actually show up in any logic book. And you may in fact recognize some of these numbers. You know, this is a 7432, a 74 LSO4. So here's a 74 LSO4, which is just an inverter, a 74 LS32, which is a quad 2-input OR gate, and the 7430 is an 8-input NAND. So this apparent discrepancy can be resolved thanks to De Morgan's theorem, which states that complementing the result of ORing variables is equivalent to ANDing the complements of the individual variables. Likewise, complementing the result of ANDing variables together is equivalent to ORing the complements of the individual variables. You can make De Morgan's theorem as complicated as you want, but it basically says that to switch between an AND and the OR gate, just invert the input signals, swap the logic gate, and invert the output signal. In logic gate form, let's clear this out of the way. It looks like this. If we OR some variables together, we will get this, that, and that is false, true, true, true. And then we complement the outputs. We would get true, false, false, false. Now, if we take the same inputs, but we complement them first, and then swap the OR gate for an AND gate, we would get this. If it's true and true, we get a true. True and false, we get a false, false, false. So this is exactly the same as that. So we can take an OR gate. We can replace that with an AND gate if we complement the inputs and we complement the output. You may have noticed that in some data books, a logic gate may be called, for example, in this TI book, a quadruple 2-input positive OR gate. Okay, so they're calling out that it's positive logic OR gate. But the logic equation is given as positive logic as y equals A or B, but they also give it as y equals the complement of A ANDed with the complement of B. And hopefully it's not lost on you that we can either complement the output of the original gate or complement the output of the substitute gate, meaning that these are equivalent functional gates. So this is an AND gate, and if we demorganize it, this would be the OR gate. OR gate, demorganized, turns it into an AND gate. NAND turns into a NOR, and NOR turns into a NAND. If you want to dig into this further, look up the principle of duality, which in this case is a rephrase of De Morgan's that if you take all the truths and replace them with falses, replace all the falses with truths, replace all the AND gates with ORs, and all the ORs with ANDs, and there you go. Now you're dabbling in negative logic. Armed with assertion level interpretation, to me, it's much easier to read and understanding some schematics. When you look at a schematic, you can think in terms of the voltage logic. So this would be an AND gate, or the equivalent would be assertion level logic. That AND, if you invert the inputs, invert the output, would turn into an OR gate. In this case, they want us to think of assertion level or functional logic. In this case, we're thinking of strictly voltage logic. Now, the absolute last thing you want to do is to take these De Morgan functional gates literally and deconstruct them into inverted inputs and inverted outputs. It's much, much easier to use assertion level logic on these. Because using assertion level logic, the understanding of the purpose of the circuit becomes easier because there's less high or low and more asserted or not. Now let's look at how this can cause trouble or at least confusion. Let's go back over here to this U7 and U8 business. If this is an I/O request during an M1 cycle, then this line U8-8, called the interrupt acknowledge, goes true. So this MC sync U7-3 will go true whenever we're in a read, a write, or servicing an interrupt. Now, if you're fortunate enough to have a narrative document for this circuit, it'll quite likely say that MC sync is read plus write plus interrupt acknowledge, where they're using the functional and negative or assertion logic to describe how to generate the MC sync signal. But let's look to see how Win Systems describe the exact same thing. In their document, they're saying that MC sync active low is generated by ORing together, read, write, and interrupt acknowledge, and then inverting that. So it's the exact same thing as before, only they're inverting both sides. So they're using assertion level logic for the input signals, but then they invert that to get the functional OR to get the active low MC sync signal. You can see it can start to get confusing. Do they mean the assertion level or do they mean the active level? Here's the exact same description and they call it out differently. They say MC sync with an asterisk, or not MC sync, is equal to the not read, ORed with a not write, ORed with a not interrupt acknowledge. But you can see this doesn't have the final inversion of the output. So the three different ways of saying the same thing. It's, tomato, tomato, I guess. Or here's another table in the prologue manual where they've basically broken that down. So instead of interrupt acknowledge, they've broken that down into its components. Here they're saying that not MC sync is equal to not read, ORed with not write, ORed with not IO request that is ANDed with not M1. Where they're using the assertion level inputs again, but now they're referring to them with the asterisk, but the end product is an assertion level output, meaning it's true is equal to 0 volts. So I'm not saying there's any discrepancy between these. What I'm saying is that you can rephrase the same thing in many different ways, and it can really get confusing as to whether you're talking about the actual logic level, as in 0 or 5 volts, or if you're talking about the assertion level. In this MOSTEC datasheet, they avoid any real pencil to paper exercise or positive negative confusion by avoiding it altogether and essentially stating things in kind of a kit form where it's up to you to decide how to assemble the kit. For example, they say the interrupt acknowledge active low is equivalent to an IO request during an M1. And technically that's correct. But they're not going to get into the nitty-gritty details of how that's accomplished. Likewise, they say that MC sync is not generated by the MOSTEC CPU cards, but if you did feel the need to generate it, gate together the read, the write, and the interrupt acknowledge. Anyway, you get the idea that once a designer and technical writer begin to implore assertion levels, it really opens the door to miscommunication, and you may really need to stay on your toes to understand the description. Usually the schematic is very clear, but the description can get really confusing. And to make matters worse, in some documentation, you may see waveforms drawn in assertion level logic. Okay, well that's all for this video. And I'd appreciate it if you let me know if this assertion level logic is still being taught, since when I'm helping people with their vintage boards, assertion level logic seems to be a consistent point of confusion. I've had people send me links to many bubble pushing videos out there where creating a De Morgan's equivalent gate seems to be thought of more of a party trick, but all the videos end before showing the real purpose and usefulness of using assertion level logic in design documentation. So I presume that if you've made it this far in the video, you found some of the information useful. As always, subscribers, likes, and comments are appreciated. Bye-bye. Talk to you later.